Hi, this is David Voss, CCIE 11372, and in this video we're covering OSPF design. We're going to begin with some concepts you need to understand, a baseline I guess you could say, prior to designing OSPF. And then we're going to get a bit more granular in this video and dig into OSPF concepts, such as administrative areas, virtual links, router types, designated routers, neighbor exchange states, link state advertisements, and best path selection. If you're going to design OSPF properly, you need to understand all of these concepts. We will not go into configuration examples that you can learn in the CCNP route exam, but for the CCDA, you will need to understand these concepts. So let's begin. OSPF is one of the most complex routing protocols that can be deployed in modern networks. OSPF is an open standard protocol, that is, it should be able to run on Cisco and non-Cisco equipment. OSPF is a classless routing protocol, and this allows it to support VLSM. Similar to EIGRP, which uses dual, OSPF uses SPF algorithm to select loop-free paths throughout the topology. OSPF is designed to be very scalable because it's a hierarchical routing protocol, using the concept of areas to split the topology into smaller sections. So it is a very popular protocol in today's enterprise networks because it can scale so well. OSPF takes bandwidth into consideration when calculating route metrics. In OSPF, it's considered the cost. A higher bandwidth generates a lower cost, and lower costs are preferred in OSPF. OSPF supports authentication, just as EIGRP does in RIP version 2. OSPF is also very extensible. It's similar to BGP and ISIS, meaning that the protocol can be modified in the future to handle other forms of traffic. OSPF discovers neighbors and exchanges topology information with its neighbors, acting much as EIGRP does in that way. Based on the collected information and the link costs, OSPF calculates the shortest paths to each destination using, as we mentioned before, the SPF algorithm. The formula for calculating the interface cost is reference bandwidth divided by link bandwidth. The default reference bandwidth is 100 megabits per second, but this can be modified, just as the link bandwidth can be modified using the bandwidth command. Please note that the reference bandwidth should be modified in networks that contain a combination of 100 megabits per second and 1 gigabit per second links, because by default, all of these interfaces will be assigned the same OSPF cost. That's obviously a big design consideration and something you certainly could be tested on. Another aspect that adds to the design complexity of OSPF is that it can be configured to behave differently depending on the topology in which you are implementing it. OSPF recognizes different network types, and this will control following actions, such as how updates are sent, how many adjacencies are made with the OSPF speakers, and how the next hop is calculated. OSPF supports the following network types: broadcast, non-broadcast, point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, and loopback. OSPF automatically selects the network type that is the most appropriate for the given technology. So for example, if you configure OSPF in a broadcast-based Ethernet environment, it will default to the broadcast type. If you configure it on a frame relay interface, it will default to the non-broadcast type. And OSPF configured on a point-to-point serial link will default to the point-to-point network type. The only network types that you need to manually assign would be point-to-multipoint or point-to-multipoint non-broadcast. These obviously are most appropriate for the partial mesh, which is hub and spoke environments, and these must be configured manually. So now that you have a high-level understanding of OSPF, let's go ahead and dig into OSPF concepts, all of which you will need to know for your CCDA exam. We're going to go through these one by one to the level of detail you need to know for the CCDA exam, and we're going to begin with administrative areas. An autonomous system is broken out into areas. So areas are a group of routers that share a same area ID, and these different areas these different groupings have different functions, and they know different types of information. So you have backbone area, standard area, etc., etc. And each of these areas perform different functions. So let's talk in detail about what some of these areas know and maybe what some of these areas do not know, but also how OSPF is designed around these concepts of areas. So remember, we're talking at a higher level here, but as a good rule of thumb, your backbone area in OSPF, if anybody ever refers to area 0, you know they're talking about the backbone area in OSPF. And this is probably the most well-known area because it is required. And all other areas must connect to the backbone area. So if for area to area communication, let's say you have an area 1 communicating to an area 3, both of those areas must connect to the backbone. So let's start here with a standard area. Now, a standard area, you know, what does that really mean? Well, standard areas can be thought of as equal opportunity employers, I guess you could say, because they know about every route in the autonomous system, in the OSPF network. And they share their routes, but they also learn all their routes from other areas through the backbone. And this is just fine. All of this route sharing is just fine if routers are high powered enough to store every route, but also to run these complex SPF calculations. But just know the standard areas contain LSAs of type 1, 2, 3, 4, and 5. Now next, if you think of a stub area, which we'll talk about next, if you think of a network, you have leaf nodes on networks. Well, that's what kind of a stub area is. It's handy if devices are lower powered, routers are lower powered, or simply do not need to know about every route. A stub area is similar to a standard area, but routers in it are not aware of externally sourced routes directly. And in terms of LSAs, that means that type 5 LSAs are not permitted in a stub area. Stub areas use a default route to exit. For traffic to exit a stub area, it uses a default route. Now, next would be a totally stubby area. And let's take this stub area concept one step further. In a total stubby area, in addition to the lack of type 4 and 5 LSAs, type 3 LSAs, which carry information about internal routes, are also prohibited. The concept of an injected default route still applies here, just like a stub area. So all traffic leaving the area does so using the default route. And then finally, let's go over this concept of not so stubby areas. So, this is an interesting, I guess you could say, concoction, because not so stubby areas can connect to non-OSPF networks that are not a part of this autonomous system, and they can receive routes from those non-OSPF networks or networks that are not participating in the autonomous system. And it will receive those routes through redistribution, and then it can turn those type 7 LSAs and kind of, basically it's going to mask them and make them appear as type 5 LSAs, and then begin sharing them onto the network. So there's your ideas of networks in areas, but all areas in an OSPF autonomous system must be, as you know, physically connected to the backbone area. Well, what if you can't do that? What if you can't connect an area to area 0? So let's draw out this concept of a virtual link. Let's imagine we have a company on the East Coast, and in this company we've deployed OSPF already. So we have our backbone area 0. And then we have other areas that have to obviously connect into this backbone area. So let's say we have an area 1 in the Boston area, and then an area 2, let's say in Florida. But let's focus in on Area 1. So in the Boston area, we have Area 1 in Boston, and we acquire another company in that area. And it's easy enough for us to connect this new company into our Boston resources. So we're going to connect them into our Boston router very simply. The problem is that even though this company that we've acquired, maybe they're already running OSPF, and we convert them to OSPF Area 3 to work within our autonomous system, we still need to meet the requirement of OSPF where an area must connect into Area 0. So OSPF allows for what is called, as you know, the virtual link. We will create this virtual link between Area 3 and Area 0. It's passing through Area 1, and this allows us to meet that design requirement of OSPF. So route to Area 3 and Area 0 see this as a direct connection, and things will work just fine thanks to the virtual link. So there are many different OSPF router types that you need to be aware of. There's the area border router, which connects one or more OSPF areas to the backbone area. There's the ASBR, or Autonomous System Boundary Router, which will be located between an OSPF autonomous system and a non-OSPF network. And then you have your backbone router, which is pretty straightforward, a router with at least one interface connected to Area 0. And then another easy concept, an internal router, a router with all interfaces in one area. Let's draw this out real quick, to drive it home. So let's draw out our Area 0. And in Area 0, you know already, is the backbone. So a router within Area 0 is a backbone router. And then we connect to another area, let's say Area 1. This is an area border router. Pretty straightforward concept. There's your ABR. And let's say we have another area we're connecting to. There's another ABR. But we are also connecting an ASBR here because we have a non-OSPF network that we're going to be injecting routes from into our OSPF process. So we are injecting routes in through an ASBR, converting type 7 LSAs to type 5, and those are being forwarded on to the network. And then you have, last but not least, internal routers, which have all interfaces in the same area. Pretty straightforward. So in order for two OSPF routers to communicate, they need to go through this process of exchange states. So you need to understand a basic concept of what these are. Here's the following states. There's the init state, where a hello packet has been sent by a router, it's waiting for a reply. Then the establishment state, where there's the discovery of that hello, and then the election of a DR in multi-access networks. The XStart stage, where a master-slave relationship is started between two routers. The router with the higher router ID becomes the master and starts the exchange, and as such is the only router that can increment the sequence number. Then there's the exchange state, where the slave acknowledges the master's packets, and this information in this state is only LSA headers, and it describes the contents of the entire link state database. Then there's loading, where there's a request for more information. In this state, the actual exchange of link state information occurs. And then there's full synchronization, and in this state, routers are fully adjacent with one another. All the router and network LSAs are exchanged, and the router's databases are fully synchronized. Now, a designated router in OSPF is a key concept that you need to know, because on multi-access networks, a designated router will establish adjacencies with all other routers on the multi-access network, learn all of their routes, and then share all of their routes with all the other routers. And then the BDR, the backup designated router, will fill in should the DR fail. And you can set the DR and the BDR manually, and actually you should do it this way. You should set it using the priority command in OSPF. So understanding OSPF priority is key, because you can manually set who the DR is and who the BDR is. Now, it's easy to talk about this and look at a PowerPoint, and you may not fully appreciate how important this concept really is. So let's actually draw it out. So on a typical multi-access network, let's say we have 5 routers and you want to establish adjacencies in OSPF to share routes between them. If they did it that way, where they're all neighboring with one another and communicating with one another, you're going to see that all of these adjacencies are going to add up pretty quickly. And that's going to tax the resources on the routers themselves, but it's really unnecessary. We can share this information in a much more efficient manner. So what we're going to do is we elect a DR, and OSPF, again, has this built in within the OSPF design itself, where on multi-access networks you can elect a DR, and then the DR establishes an adjacency with all the other routers on the multi-access network. It learns all of their routes and then shares all of their routes. So now we just have 4 adjacencies required. Now if the DR fails and those adjacencies fail, the BDR would take over. Now regarding link state advertisements, what you really need to know, at least just for now in OSPF, is that a link state advertisement is a packet that contains all relevant information regarding a router's links and the state of those links. Now there are many different types, and I've listed the key types for you here. And we're going to dig into detail on these different types as we get into the labs. But just for now, know that these are informational packets that have information on a router's links and the state of those links. So now that OSPF has gathered all this information, it needs to know what to do with it. It needs to choose the best path. So it puts all the information in a topology table. And then OSPF, the metric for OSPF is cost. So cost is 10 to the power of 8 divided by bandwidth, and lower costs are preferred. So the best way to understand cost is actually for us just to draw this out to see how it works. So let's draw out a 6 router network. And let's say we have router 1, which ultimately wants to communicate with a network off of router 6. And it will have 2 choices, 2 paths it can possibly take. It can go via router 2 or via router 4 to this network. We'll say 192.168.10 network/24. Which is hanging off router 6. Now, router 1 then calculates using OSPF the cost for each and every link in this path. And it's going to do the same for the path from router 2 and 3 to 6. And then what OSPF is going to do is add up the entire cost to get to router 6. So from going via router 4, that path has a total cost of 20. And going via router 2, that path has a total cost of 25. And we know that OSPF uses the lower cost to make its decision on which path to take. So the total cost of 20 wins out, and we will choose router 4. Now that being said, let's say a new network is introduced that has higher bandwidth links. And even though we have more routers or more hops through this network, let's say there are 4 hops. If the cost is low, and for this case we'll say 5, 5, 1, 1, and 1. If the total cost here is just 13, even though there's more hops, OSPF is going to choose this path because it's more efficient. So that's cost basically explained. That's cost in a nutshell. So here's what you've learned. You've received an overview of OSPF, and then we got a bit more granular to the level you'll need to know for the CCDA exam, including administrative areas, virtual links, router types, designated routers, neighbor exchange states, link state advertisements, and best path selection. I'm confident after watching this video, if you know this information well, you're going to do excellent on the OSPF portion of your CCDA exam. Good luck in your studies.